When a ship capsizes, the public often blames a storm or a rogue wave, but the most insidious threat can strike in calm weather. Cargo shift, a single container breaking loose, or a sloshing liquid in a half-filled tank can silently steal a vessel's stability. But how can a few tons of shifting cargo doom a vessel weighing thousands? The answer lies in a ship's stability curve, a graph that measures its righting arm. When cargo shifts, that arm shortens, and the ship's metacentric height, or GM, can drop to zero. At that point, the vessel becomes a floating pendulum with no will to return. The International Grain Code was written in blood after the Kristi disaster. Yet even today, over half of cargo ship losses stem from cargo shift or flooding. This is not a problem of ancient ships. It is a modern, silent killer that demands our attention. So what keeps a ship upright? The answer lies in a single number, the metacentric height, or GM. This invisible point, like a pendulum's pivot, determines whether a vessel rights itself or rolls over. A positive GM means stability. A negative one spells disaster. Engineers plot this stability on a GZ curve, a graph that shows the ship's righting arm at each angle of heel. As long as the curve stays positive, the ship can recover. But when cargo shifts, that curve flattens and the margin for error vanishes. Now picture a container ship in calm seas. A single stack of containers breaks loose, sliding across the deck. That shift moves the centre of gravity sideways, shrinking the GM. The ship lists and the crew scrambles to correct it. But the damage is done. That is why stability curves are mandatory under SOLAS. Every cargo ship must carry a stability booklet, showing the GM for every loading condition. But a booklet is only as good as the crew's understanding. And in the chaos of a shift, numbers on paper mean little. But here's the real danger: free surface effect. Imagine a partially filled tank on a ship. When the vessel rolls, the liquid sloshes from side to side, and that sloshing creates its own force, pulling the ship further over. It's like having a giant pendulum inside the hull, swinging with every wave. So how much damage can a little sloshing do? The answer lies in a simple rule. The free surface effect is proportional to the cube of the tank's width. That means a tank just twice as wide creates 8 times the destabilizing force. The International Maritime Organization warns that this effect can cut a ship's metacentric height by up to 50%. Now consider a container ship with dozens of partially filled ballast tanks. If the crew fails to properly ballast, the free surface effect from just one wide tank can reduce stability enough that a moderate wave tips the ship past the point of no return. The vessel becomes a giant pendulum, swinging wider with each roll until it cannot recover. And this is exactly what doomed the MV Cougar Race in 2006. During a routine ballasting operation, crew left tanks partially filled, creating a massive sloshing effect inside the hull. The ship listed to 60 degrees in calm waters. Rescuers found it drifting sideways, a silent monument to a danger that lurks in every half-empty tank. So why do ships capsize in seas that seem calm? The answer is an invisible killer: parametric rolling. When the length of a wave matches the ship's beam, the vessel can begin to roll with increasing amplitude, even in moderate swells. The American Bureau of Shipping warns that parametric rolling can induce rolls of 40 degrees in calm seas. That is enough to snap container lashings and send stacks tumbling like dominoes. The ship does not need a storm. It only needs the right wave, which means a ship can be perfectly stable on paper. Yet in a following sea, the wave train synchronizes with the hull's natural frequency. Each wave adds to the roll, and within minutes the vessel's heeling past 30 degrees. The crew has no warning. And that is exactly why parametric rolling is so insidious. It does not announce itself. The sea looks manageable. The stability booklet shows a safe GM, but the ship is caught in a resonance that no curve on paper can predict. By the time the crew realizes, containers are already lost. So why did nobody stop the El Faro from sailing into a hurricane? The crew miscalculated stability. On October 1st, 2015, the 790-foot container ship departed Jacksonville, bound for Puerto Rico, with a deck load of containers improperly secured. The crew had a stability booklet. They calculated the GM at 3.2 feet, well above the minimum. What they missed was the sloshing from partially filled ballast tanks, which eroded that margin with every wave. Then the hurricane hit. Waves over 30 feet pounded the hull, and the deck cargo shifted. The center of gravity moved, the GZ curve flattened, and the ship began to list. Within hours, the list reached 20 degrees, then 30, then 50. The NTSB report concluded that the crew's failure to account for sloshing in ballast tanks and cargo shift led to a loss of stability. All 33 crew perished. The El Faro became a grim lesson. Stability curves are only as good as the people who read them. So why did nobody stop it? The International Grain Code was written in blood after the 1978 Kristinaki disaster, when a grain cargo shifted and capsized the ship in minutes. But a code is only as strong as its enforcement. Under SOLAS, every cargo ship must carry a stability booklet and follow strict loading procedures. Yet over half of all cargo ship losses from 2001 to 2010 were due to cargo shift or flooding, according to Allianz. The problem isn't the rules, it's the humans who ignore them. The International Grain Code was written in blood after the Kristinaki disaster. That phrase echoes through maritime history. Regulations born from tragedy, yet still ignored. So what lessons can we draw from these tragedies? First, stability curves are not abstract math. They are a lifeline. Sloshing in tanks and parametric rolling are invisible threats that can sink a ship in calm water. Understanding them is the difference between a safe voyage and a disaster. But cargo shift isn't limited to containers sliding on deck. In bulk carriers, grain or ore can liquefy and flow like water, creating a sudden free surface that can capsize a ship in minutes. This phenomenon, known as liquefaction, has claimed dozens of vessels. Liquefaction occurs when moisture in cargo causes solid particles to behave like a liquid. The International Maritime Organization estimates that over 60 bulk carrier losses since 2000 are linked to liquefaction. It's a hidden hazard that turns solid cargo into a deadly wave. So how does liquefaction happen? The cargo's moisture content exceeds its transportable moisture limit, causing the solid particles to lose friction. The cargo then behaves as a liquid, sloshing with the ship's motion. This can reduce a ship's GM by half in moments. Consider the 2009 loss of the Stolt Valor. The chemical tanker capsized off the coast of India after cargo shifted in heavy weather. The crew had no time to react. The ship sank in minutes, and 18 of the 22 crew perished. The stability booklet was useless against the sudden shift. But why do crews fail to prevent these disasters? Often it's a lack of training. Many seafarers are not adequately trained to interpret stability curves or understand sloshing effects. A 2018 study found that 40% of officers could not correctly calculate GM from a stability booklet. This training gap is a systemic issue. The standards of training, certification, and watchkeeping code requires basic stability knowledge, but the practical application is often neglected. Simulators can help, but many shipping companies cut corners to save costs. The cost of this ignorance is measured in lives and cargo. Allianz reports that cargo shift and stability failures cost the shipping industry over $500 million annually in claims. But the human cost is far greater. Every loss is a family shattered, a crew lost to a preventable tragedy. Cargo shift remains the silent killer, but it is a killer we can outsmart. Every crew member who reads a stability booklet, every officer who checks tank levels, honours the 33 lost on El Faro. The sea demands respect, and understanding the unseen forces is the first step to survival.